Is screen visible? I want someone to acknowledge. Is the screen visible?
Yes, sir.
Yes,
Fine.
sir.
So some audio issue is there. Am I audio? My audio is okay. Is
Yes,
my audio
sir.
is okay?
Yes, sir.
Okay. Just 1 second. 1 second. Some other issues. It's because people are joining. Some issue with S10s for many people. I'm just checking it out. Yeah, good number of people are there. Let them come. Just 1 second. Fine. So once again, good morning to one and all those who are attending this online session. Hope the first hour went on smooth. Second hour now you are attending the power electronics and instrumentation. Today we are going with the new model. So let me share my screen. So this is the module number 2, where the module number 2 is deals with the phase control converter and choppers. And model number 3 deals with inverters. So first of all, we should know converters and usage of those converters. And next we have to go for the inverters. That is module 3. So these two are a little bit simple, where you can easily go through some of the applications and how exactly your converters are going to perform converting AC to DC. So the basic, straight away I'll move on to the other slide. So this is what the slide which gives you what exactly module 2 is. Phase control converter, we call that. So in this one, what are the different types of control techniques we have for converting AC to DC? Converter is basically AC to DC. Even DC to DC converter is also there. DC to AC converter is also there. Okay. So we thoroughly discuss about the different control techniques, and after that we go for single phase off wave control rectifier, and after that we go for single phase full wave control rectifier with resistive and inductive loads. We'll be having the resistance, we'll be having the inductance as a load, and if these two are the loads, what we can get, we are going to check it out. And effect of freewheeling diode. So there is a freewheeling diode, the operations of freewheeling, how exactly a freewheeling, what do you mean by freewheeling, and how it is going to perform your conversion. And after knowing all this power conversion, then we go for the choppers, different types of choppers, classifications of the choppers, basic operations of the choppers, step down chopper, step up chopper, and also step down and or step up choppers. Means both. It can go either you can perform step down or it can go for step up. So this entire thing is called as one module, that is power converters and choppers. The basic CO, what we are going to come across is analyze and design the control rectifier. First of all, we are going to analyze what you mean by rectifiers, then what you mean by control rectifier, then we are going to analyze that how exactly we can design it. So we can design on our own. What are the basic components are required? If only diodes, if you are using, what is the purpose? If with thyristor, if you are designing the rectifiers, what exactly we are going to get, and what is the performance of that one? And if you are providing some load as resistor or load as an inductor, what we are going to get. So these are the topics. We'll move ahead. So introduction of power converters, phase converters, or for power converters we can call that. Process of converting AC to DC is basically power converters. As I'm keep on telling you many times, we have power generations. Most of the time it is in the form of AC, but sometimes I need DC, so I need to convert AC to DC. This can be achieved by variety of circuits using switching devices. Switching devices Either you can use thyristor, you can use diode, you can use some other devices where we can perform AC to DC conversion. Widely used switching devices are diodes, thyristors, power transistors, power MOSFETs, etc. That is metal oxide semiconductor devices. Basically, we have three different classifications of rectifier. First one is uncontrolled rectifier, second one is fully controlled rectifier, and the third one is off controlled rectifier. Uncontrolled rectifier, it uses only diodes, only simple diodes, what we are having, what we did in the lab. So there are simple diodes are going to be used where we don't have the controlling. It's some uncontrolled. What do you mean by uncontrolled? In the sense, we will be having some ripple, we'll be having some pulsating DC. So we'll not have a fully 100% DC over there itself. So if you want to go for the fully controlled rectifier, then we can go for some thyristor, where thyristor is mainly for controlling purpose, as we have discussed in the previous session. We can control the operation. Okay. And similarly, there's a mixture of diode and thyristor where it is off control, because diode is not at all controlling, thyristor is fully controlling. If we put them together like an hybrid, diode and also thyristor, we will call them as off control rectifiers. So these are the major three classifications of the rectifiers. Hope everything is going on smooth. No issues. If any issues are there, you can raise the question. You can say that there is no audio slide, or you can check it out. Just 1 second. Let me see. Okay. Okay, we'll move ahead. So when you go for the rectifiers, it is possible for a phase controlled converters provide either a 1 quadrant or 2 quadrant, 4 quadrant operations at the DC terminals. See what happens now, when we are converting the power from AC to DC, we are going for a phase control. We want to control the phase. So when you are performing the phase control, either you can get the 1 controlled output, or you can get the 1 quadrant operations. You can get the 2 quadrant operations or 4 quadrant operations. So first of all, we should know what I mean by 1 quadrant and 2 quadrant and 4 quadrant operations. Okay, so let us see. Basically, uncontrolled and off controlled rectifiers will permit power to flow only from the AC system to DC load. That is unidirectional converter. See, there are three basic classifications: uncontrolled, fully controlled, and off controlled. In that one, uncontrolled and off controlled, where only one direction it will go, that is AC to DC conversion only, it's going to perform. But when you go for the fully controlled rectifiers, it is possible by control of the point on wave at which switching takes place. It is switching, it is a spelling mistake is there. Switching takes place to allow power to be transferred from DC side to the AC side. That is DC side of the rectifier back to into the AC side, where the reverse operation also is possible. DC to AC converters, where we will call them as inverters, or bidirectional converters we'll call them. Off controlled and uncontrolled, there is only one direction, that is AC to DC. Fully controlled, it performs AC to DC, and also DC to AC also is going to perform. So let us go ahead. What exactly our rectifiers, our phase control rectifiers are going to work. So here is the just glimpse of what you mean by 1 quadrant, 2 quadrant, and 4 quadrant, and how the circuit is going to be. What are the elements we will be having over there? As we have seen in the previous slide, if it is 1 diode and 1 thyristor, we will be having 1 quadrant output operation, 1 quadrant operation. This is for rectifier, it works as a rectifier, and it will be 1 quadrant operation. We are having a AC input, we are having a DC output, we will be having a SCR and also a diode in the circuit. We call this as 1 quadrant converter. We call this as 1 quadrant converter, where AC to DC conversion is going to happen. But when you go for the 2 quadrant converter, we'll be having only SCR, only SCR, will not be having the diode. AC to DC conversion is going to happen. Here you see, it can work as an inverter, it can work as a rectifier also. It can work as a inverter. At the first quadrant, it is working as a rectifier. At the fourth quadrant, actually it is basically two quadrants. So the location is quadrant and fourth quadrant. At this fourth quadrant, when it's operating, it will be converted. It will be considered as an inverter. So thyristor we are having where AC input signal is there, DC output signal is there. Okay, where it's going to convert at first quadrant, it will work as a rectifier. At the fourth quadrant, it will work as an inverter. Similarly, we will be having two thyristor model. Two thyristor model. It is double than the second one. See, the second one is only one thyristor. In the third one, we're having two thyristor. They are connected in the opposite direction. So AC to DC, okay, it's going to convert one quadrant, that is rectifier, and other quadrant is going to work as a inverter. Similarly, when you go for the second converter, where converter 2 is here, where it's going to perform at the uh, northwest. I'll just go in this direction, northwest or top left. It will be converter 2. We'll call as a converter 2. It works as an inverter. Similarly, we'll be having at the what we can call third quadrant. We'll be having rectifier. It works as a rectifier. That means one thyristor can perform two quadrant operation. Other thyristor can perform other two operations. Totally, we are going to get four quadrant. So here the conclusion is, if you rank thyristor and diode, it is one quadrant. If you rank only one thyristor, it will be two quadrant. And two thyristors, you will be having four quadrants operation. You are going to have that. Any issues? Okay, some people are still entering. So this is three different types of phase controlled operations, phase controlled converters. One is one quadrant converter, other is the two quadrant converter, other is the four quadrant converters. So moving ahead, one by one, we'll check it out. How exactly a control techniques, how exactly we can control. So basically a simple off wave control converter using unidirectional switch. This is a unidirectional switch. We are going to perform off wave control converters. It's a figure shows we'll be having an inductor, we'll be having a resistance, a load as a load, and we're having an input AC supply, and we are going to get the measure the voltage across this one, where we are going to get off wave control conversion. We'll see step by step. We are going to check it out how exactly it's going to convert them. So control techniques, they are going to control your input and they're going to convert them into required output over there. See, first one, phase angle control. This we have already discussed in the previous session also. Here what happens, we have a input voltage supply voltage, it is an AC. The load voltage, the voltage across the load, because it takes some time to triggering time. That's why we call firing angle control. Till the firing angle comes, there is no voltage. Once the firing angle comes, then you are going to output. It's going to be the voltage what we are going to measure across the load. You are going to get like this. So you will not get the fully off waveform. You are going to get only after the triggering angle, after the firing angle only you are going to get that. In the second half, it is totally zero. It works as a half wave rectifier, so you will not get that one. Because when the input voltage is reversed, you are not going to get the input signal. If it is in negative direction, you are not going to get any signal over there. Once it crosses 2F, that is 360 degree, once again it starts in the positive direction. Once again it's going to be a firing angle, it's going to check. Until the firing angle is there, you're not going to get the output. Once it crosses the firing angle, this your triggering angle or voltage for triggering your thyristor or a component where Until then, you're not going to get the signal. Once it crosses, just wait. People are in the lobby. Control voltage EC. So where it's going to be for SCR. If any SCR, if you're using the control voltage till alpha, we will not get any voltage. Once it's, that is your trigger gate pulse, we call that one. Once this pulse has been given, then afterwards only you're going to get the control voltage EC for SCR, and control voltage for MOSFET and IGBT and BJT. This is how it's going to come. For SCR, you're going to get as a pulse. For other devices like MOSFET, IGBT, and BJT, you're going to get a wide signal, a wide pulse. This is a very narrow pulse for SCR. For other devices, you're going to get a wide pulse till the end of the half wave. So this is phase can be controlled. Phase angle can be controlled over there. People are still admitting. Okay, this is the first technique, control techniques, where we can control the pulse, or we can. Second technique, we go for the excitation angle control. So it is it is after 90 degree. Previously it was before 90 degree, it was coming over there. Here it is going to be after 90 degree. Supply voltage is same. Load voltage, it is excitation angle. Input, as the input comes, it's keep on. Once you give the once you want to go the pulse trigger switch, it will go. That is here the beta value is where you are going to, you will not get any signal for the first half, and second half as usual you will not get the signal. Once again, in the first half, if it comes excitation comes, a load voltage can be measured over here. Here for pulse trigger switch, level trigger switch, there are two different switches are there, pulse trigger and level trigger. Once the level has been changed 1 to 0, that is level trigger. Here the pulse, in the sense, once the pulse is initiated, that is pulse trigger. A small pulse, it is initiated, that is pulse trigger switch. Here the level trigger switch, in the sense level is changing from 0 to 1, high to low, low to high, high to low, low to high. So at that time it's going to be. So initially, what are the load voltage EDC is there? Same voltage will be appearing in for the level trigger switch. Once the load voltage decreases to 0, your control voltage also will be decreases to 0. So here, when it is pulse trigger switch, it is once the pulse is there, it's going to trigger. Once the pulse has been given, it's going to trigger. That is why excitation will call that one. Excitation angle can control, we'll say. So first one is phase angle control. Second one is excitation angle control. And the third one is pulse width modulation. So this is very much important when you come to the communication subject, analog communication, digital communication, like that you're going to get. So as we have seen, first of all, we should know about the modulation. Then only we can go for pulse width modulation. Modulation, carrying the actual signal from one end to other end using a carrier signal. See, I want to, it's like a simple example given when one of the resource person is, he said, I have a food, I need to carry the food. So food is the actual data you want to carry. So if you want to carry from one place to another place, you'll be having a container. Without the container, I cannot carry the food. No one can carry that one. There should be a proper container to carry the food from one place to another place. Then once it carried, once it reaches the destination, then you will take out the food and eat it over there. You will not eat the carrier. The container is only to carry from one end to other end. So that is what a modulation means. Modulation is, I have an actual information. That actual information need to be transferred from one place to other place. Since the information cannot go as it is by its own, we need to have a one more very strong signal called a carrier signal. See, one more example I can give. I need to travel from my home to college. It is some around some distance is there where I cannot go on my own walking. By walking, I cannot reach over there. I need a vehicle which can carry me from my home to the college and it can drop me over there. Vehicle is just to transfer a person from one location to another location. Similarly, in your information, analog communication or digital communication, what it may be, any information need to be transferred from one place to another place. It should be carried by some other strong signal. So we call this a carrier signal. Combining the actual signal with the carrier signal is called as a modulation. Modulation is my input signal and combined with that one carrier signal put together is called as a modulation. So in that one type of modulation is pulse width modulation. Pulse width modulation. Width of the pulse will take care of how exactly the signal can be modulated. So based on the width of the pulse, we can modulate the actual signal and we can carry that from one location to another location. In our case, in our syllabus, pulse width modulation control means we are able to control the input signal or we are able to convert from AC to DC by using. Hope they. Is everything is okay? I need some acknowledgement from your end. Anyone? Because I'm working with my mobile data. As soon as a call comes, there may be some issues. Kindly acknowledge.
No issues, sir.
Okay, thank you. Thank you. So I was discussing about the pulse width modulation. I had given some brief introduction about what I mean by modulation and what I mean by pulse width modulation. Here, the control signal is a pulse. We're going to give a pulse. Based on the pulse, we're able to modulate, and based on that one, we can control the you can convert. There is control and convert, both you can go for it. So I'm having an input signal, I'm having some pulse, and this is not a pulse. Here is the pulse comes into picture, turn on pulse and turn off pulse. Turn on pulse and turn off pulse comes into picture. So based on these two, see it's a turn on pulse and this is a turn off pulse. See the lines across this. As soon as your turn on pulse started, your control voltage is initiated. Similarly, as soon as your turn off pulse is started, your signal is off. So this is a turn on pulse and this is a turn off pulse. Based on these two pulses, there is pulse width modulation. I'm able to get the trigger. There is control voltage, the level trigger comes into picture. Here they are given the time, that is pi by 2 minus delta by 2, pi by 2 plus delta by 2. So that is pi by 2 is what? 90 degree minus delta by 2. Similarly, 90 degree plus delta by 2 they have given. So that is what your width of your pulse and width of your pulse. Based on that, my signal can be controlled. So this is input signal, this is the control signal. Based on the two pulses, that is turn on pulse and turn off pulse, I'm able to control that. In the second half, I don't give any turn on pulse and turn off pulse so that my output will be 0. Similarly, when you go for repetition, same thing comes into picture. There is pulses which are used for triggering. Turn on pulses and turn off pulses which are used for triggering Based on this, I can control my signal. So that is what pulse width modulation control. One is phase controlled. Second one is there is firing angle control. We'll call that one. Second one is excitation angle control, and third one is pulse width modulation control. Fourth one, that is single phase off-air rectifier. It's not the fourth one. Three different types we have checked it. Now we are going for rectifier. We know what is rectifier. We have studied the rectifier. We have executed the rectifier in the lab, but that is using a diode. But the same experiment we are conducting using a thyristor, where I need to control single phase of a controlled rectifier. We need to control the data. We need to control the signal over there. So almost same as your off-air rectifier using diode, but the only major difference is instead of diode, I am using a thyristor, and we are having a load, resistive and inductance load. Clearly, it is mentioned in your syllabus saying that one with resistive and inductance load. We are having resistive and inductance load, and we are going to measure the output voltage across these two. So this is AC power supply, transformer, step down transformer. 230 volts will be step down to 15 volts or 30 volts or 12 volts like this. And that 12 volts AC, we are going to give it to a thyristor, and it is AC signal. E is equal to EM sin WT, and we need to excite. We need to give a firing angle. We need to excite this one, okay? Or we need to go for applying the thyristor input, I gates pulse. Once gate pulse has been given, then the thyristor starts working. Based on that one, my ID. Okay, the current will flow here, and we're able to measure the EDC. This is off-wave control rectifier with RL load because it's only one thyristor we have used over there. Off-wave only can be transmitted because only half cycle, second half cycle is going to be 0. How it is? This is what the diagram. This is what the waveforms we are going to get. Input is there, and triggering pulse is there, firing pulse is the IG, where firing pulse, once the firing pulse has been given, then only your thyristor is going to start working. Till then, thyristor will not conduct. Thyristor works as an open circuit. Once it has been, firing angle has been given, then your load voltage can be measured over there. So as the input increases, the load voltage increases. From there, it's keep on decreasing. Once it comes near to pi, or pi, exactly pi, okay, you're going to get, because it will be going below that one also. There is up to some negative value, then it will come back to 0 because the load current is there. ID, load current, it increases when it is in positive direction. When it is in forward bias, load current is keep increasing, and once it is negative bias, that is reverse bias, current decreases. Since the current decreases, your load voltage also it goes negative. Then once it becomes 0, load voltage will become 0 over there. So input signal, this is your triggering pulse for triggering your thyristor, and this is your load voltage, that is output voltage across the resistance and also inductance. Then load current we are going to measure over there. Voltage across the SCR. This is voltage across the SCR. We know that for voltage across the SCR will be initially it's going to be keep on increasing until you give the triggering pulse, then it's going to be 0. So it's going to become 0 and it will become negative, and one side starts going towards the positive. Once it reaches the pulse, that is IG is been given, from there it once again. This is same as what we have explained in the previous session also, how exactly thyristor is going to work. So very simple, but we should know what you mean by IG, how exactly IG has been given, at what time IG has been given. From there, my outputs, that is EDC, can be measured over there. So simple off-wave controlled rectifier. Okay, off-wave controlled rectifier using a thyristor. Now, with resistive load, if it is a resistive load is there, what's going to be the equation? How exactly we can measure? Single phase off-wave controlled rectifier with resistive load, average load voltage. The average load voltage can be derived as, that is load voltage EDC. You can go for EDC. The average load voltage can be derived as, EDC is derived as 1 by 2 pi integral of your input waveform EM sin omega t dt. See here, this is the input waveform. Em sin omega t, we are going to have that one. We are going to integrate Em sin omega t, actually Em sin omega t into derivation of omega t, where Em is the peak voltage of the AC signal, which is equal to, when you go for integration, 1 by 2 pi Em into minus, when you go for integration of your sin omega t, you're going to get minus cos omega t pi to alpha. There's a pi to alpha only they are given over there. Is supposed to measure. So which will be equal to, when you go for integration, you'll get 1 minus 1 plus cos alpha. Em divided by pi, 1 plus cos alpha. You should know what is the value of cos pi and what is the value of alpha, what are the angle you're going to give. Cos pi is going to be 1, and you're going to have alpha. So 1 plus cos alpha. The maximum output voltage is obtained when alpha is equal to 0. When alpha is 0, you're going to get maximum. When alpha is having some value, you're going to keep on decreasing over there. You'll get the decreasing. So EDC maximum you're going to get when you're going to have the EM divided by pi. The maximum output voltage you're going to get EM divided by pi. Now let us see. EM divided by pi. There is a maximum voltage we are going to get. So voltage, the maximum you will be getting EM divided by pi. So you can get the voltage across this one. This is the voltage. Average load current, the current through the load, we will be having the average load current is directly proportional to the average load voltage divided by the load current. So we are having the equation, whatever the load we are having, divide by that one, immediately you are going to EM divided by 2 pi into 1 plus cos alpha divided by R. R is a load. So with resistive load, if you are having only resistive load, the RMS load voltage for a given firing angle alpha is this one. Chandana. People are still adding, still joining. So RMS load voltage for a given firing angle alpha is given by, you should measure, you should give the same thing, that is RMS value. RMS value means it should be square of that. Okay, 1 by 2 pi alpha to pi Em sin omega square d omega t, root of that entire root of this entire thing. There is what you're writing E, your EDC, root of EDC, you're going to get that one. So it's been given, integrate them, you'll get the value. Finally, for firing angle alpha is equal to 0, EM is equal to EM by 2. So you have to integrate, you should substitute the values, keep substituting when you go for sin omega t. So EM is going to be, it's a constant value, take it out, EM square. Okay, and sin square omega t, when you go for sin square omega t, it will be 1 minus cos omega t divided by 2. And take 1 by 2 pi, EM also taken out, EM square is there, EM has been taken out, now EM has come out. So square root of EM square is EM, 1 by 4 pi. You're going to get 2 also outside, 2 also outside you take, then you're going to get integrate them. Omega t minus sin omega 2 divided by 2 pi by alpha, you will be getting ERM is equal to final stage, it will be EM by 2. So it is very clear, the RMS value, what you are going to get, it is EM by 2 only. So we should know, if I am using a half wave control rectifier, if I am going for that, what should be the average load current, what will be the average load voltage, the voltage across the load, the current through the load, and RMS load voltage also you should measure that one. This is with respect to single phase half wave control rectifier. So the same thing has been given. What is the gate pulse of T1? What is the gate pulse of T2? Within that, you are going to get the signal. This is V0, this is I0, this is your input. Okay, this is the V0 you are going to get, this is I0 you are going to get. Triggering pulse 1, triggering pulse 2. Within that only you are going to get the value. So you will not get negative signal, you will not get negative signal, you are not going to get. Only triggering plus 1, positive, negative, positive, negative. Within that, you will not get, you're not going to half wave rectifier, you are not going to get the negative signal. I mean, during the negative off cycle, not going to get the signal over. Principle of phase control. What exactly phase control? In phase control, the thyristors are used as switches to connect the load circuit to the input AC supply for a part of every input signal cycle. So the thyristors are used as switches to connect the load circuit to the input AC supply for a part of every input cycle. That is, the AC supply voltage is chopped using thyristor during the part of each input cycle. Means we are going to chop it out. We are going to remove AC signal only depending on the half wave or full wave. Whether you are having only one thyristor or you are having two thyristors, where exactly it's connected, we are going to chop them. Thyristor switch is turned on for a part of every half cycle, so that input supply voltage appears across the load and then turned off during the remaining part of the input half cycle to disconnect the AC supply from the load. That is what the operation. By controlling the phase angle or the triggering angle alpha, that is delay angle, the output RMS voltage across the load can be controlled. So RMS voltage can be controllable. The trigger delay angle alpha is defined as the phase angle. This alpha is a phase angle, the value of omega t, at which the thyristor turns on and the load current begins to flow. Now, the basic principle of AC phase control technique is explained with reference to a single phase half-wave AC voltage controller, unidirectional control circuit shown in the here. Okay, shown below. This is what your input. You're going to have this is negative. Okay, diode is negative. Half-wave AC phase control rectifier. The thyristor is going to control over that. Half-wave AC control uses one thyristor and one diode connected in parallel across each other in opposite direction. That is, anode of thyristor T1 is connected to the cathode of the diode D1, and the cathode of T1 is connected to the anode of the T1. So it is like here. Anode of the T1 is connected to cathode. Cathode of this one is connected to anode. The output voltage across the load resistance R and hence the AC power flow to the load is controlled by the varying the triggering angle alpha. So how we can control? By varying the triggering angle, we can control them. The triggering angle or the delay angle alpha refers to the value of or the instance at which the thyristor T1 is triggered to turn on by applying a suitable gate trigger pulse. So how exactly we can go for the triggering angle? Suitable gate pulse we should apply for the thyristor. So it will trigger your thyristor. It's going to perform the operation. That is where your triggering angle comes into place. Thyristor T1 is forward biased during the positive half cycle of the input AC supply. That is correct. It can be triggered made to conduct by applying a suitable gate trigger pulse only during the positive half cycle of the input supply. That is also. When T1 is triggered, it conducts and the load current flows through the thyristor T1, the load and through the whatever the current you're having, it passes through the T1, it will go to the load and also through the transformer secondary winding. By assuming T1 as an ideal thyristor, assume that one is ideal thyristor switch, it can be considered as a closed switch when it is on during the period omega t equal to alpha to pi radians. The output voltage across the load follows the input supply voltage when the thyristor T1 is turned on and when it conducts from omega t alpha to pi radians. Same thing is repeated. When the input supply voltage decreases to 0 at omega t is equal to pi for a resistive load, the load current also falls to 0. Whatever I explained in the waveform, the same thing has been explained here as step by step. Between the time period that is omega is equal to pi to 2 pi, when the supply voltage reverses and becomes negative, diode D1 becomes the forward bias and hence the turn on and conducts. The load current flows in the opposite direction during omega t pi to 2 pi radians when D1 is on, and the output voltage follows the negative half cycle of the input supply. So see here. Here it's going to be triggering angle is checking because thyristor has to work. In the second half, diode is going to work. Here gate pulse has been given so that thyristor will work. Until then it will not work. So first half. So you are controlling negative because diode is working. Diode is forward bias. Through the diode is going to perform that pulse. Disadvantage of a single phase half-wave AC voltage control rectifier. The major disadvantage of the output load voltage as a DC component because the two halves of the output voltage waveform are not symmetrical with respect to zero level. Definitely. See here, they are not symmetrical. This is starting at this point because the triggering angle because of the alpha, but this is different. This off is totally different with this off. So we will be having two different levels. The output or load voltage as a DC component because the two halves of the output voltage waveforms are not symmetrical with respect to zero level. The input supply current waveform also has a DC component which can result in the problem of core saturation of the input supply transformer. That is also one of the disadvantages because AC will be having a DC. The input supply current waveform also has a DC component which can result in the problem of core saturation because we cannot go for a saturation. There is some fluctuation comes into this. The half-wave AC voltage control using a single thyristor and a single diode provides control on the thyristor only in one half cycle of the input supply. Hence, AC power flows to the load can be controlled only in one half cycle. That is why. Because I can control only in the first half cycle. Since the diode is available, I cannot control in the second half cycle. That is what is being given. Half-wave AC voltage control gives limited range of RMS output voltage control. That is one of the major disadvantage. We don't have the fully controlled RMS voltage, limited range. Because the RMS value of the AC output voltage can be varied from a maximum 100% to Vs at a triggering angle alpha is equal to 0 to a low of 70.7%. 100 to 70.7% we can vary that one. Which one? The RMS value of the AC output. These drawbacks of a single phase off-wave AC voltage controller can be overcome by using the single phase full wave AC voltage controller. So off-wave AC controller is having a disadvantage that can be overcome by using a full wave AC control rectifier. I will explain that one in the next class. This is single phase full wave AC control rectifier. See, we are going to have the two thyristor here. In half-wave AC control rectifier, we are going to have only one thyristor, but in single full-wave rectifier, we are going to have two thyristor instead of a diode. I'll explain that one later. This is the session for now. Any questions, any clarifications, you can raise and you can ask me. Any clarifications? Any doubt? It's because on